Now is it working? Okay. So it's our great pleasure to have Peter Galison today from the History of Science department. And of course, this is wonderful to have this course at the historic moment in the history of black holes when we just in the middle of the lecture, we saw them for the first time. And Peter was involved in that collaboration, or is. And we've had several lectures on various aspects of that. Shep came, and we talked about the shape of the shadow and so on. But now for an even broader sweep, Peter's going to go back to the beginning and try to put this whole amazing thing that we've been discussing in this course and the stuff that's happened in the last few weeks into a broader historical context. So take it, Peter. And we're going to end at 5:45. Yeah.
So I want to go back to early days of black holes and to track some of the high points, but also mention some of the low points of the history of black holes and the stages that I see as being marked out over this course of events. I remember taking general relativity in this room as an undergraduate, and at the time my professors here were split on whether black holes were real or not. So it was things have happened fast, actually, in the longer scheme of things. So Einstein, as you've probably discussed in great detail, worked out his general theory of relativity, building on what he'd done with special relativity and a lot of work as he came to think about the idea of space-time and expanded notions of symmetry that came out of special relativity, as he wanted to consider a broader range of types of motion or changes of coordinate system. And by 1915, he finally, after many false starts, corrections, and adjustments, had his equations, his eponymous equations. And almost immediately, this is in the middle of World War I, Einstein had left Germany angry at the Prussian militarism that he thought had infected the world around him. As a 16-year-old, he renounced his German citizenship. He went to Italy. He came back. Finally, right around the beginning of World War I, but with the understanding that he was he was a pacifist. He was one of the few vocal pacifists in Germany, and this had actually some physics consequences. Eddington, whose famous expedition showed the bending of starlight and confirmed one of the three great predictions of general theory of relativity, was a pacifist in England and much maligned and attacked during World War I. And Eddington made his expedition in part as a gesture of international solidarity against war. And he began his planning in World War I, deliberately designed to check a German pacifist's theory. It was not just a random choice for Eddington. But in 1916, so right after Einstein was writing up his summary paper, this was after the theory itself had come out the year before, Karl Schwarzschild was strongly identified with Germany. He was proud of his German citizenship. He was not at all right-wing, but he believed in the country. And he went off to the front, and he was indefatigable and incredibly brave. They saw various generals coming back the other way from the front as he was going towards it, and he was calculating rocket trajectories and in some ferocious fighting. As a child, he was we know him for the Schwarzschild solution, or you know him for the Schwarzschild solution, but he had done many other things. He began calculating detailed problems in celestial mechanics as a child of 16 or 17. He got interested in non-Euclidean geometry long before general relativity and began to think about ways that it might play a role in physics. He was interested in photography. He developed theories of the emulsion and astrophotographic imprints on photography and how it might be used. And he began to think almost immediately on the development of general relativity about redshift tests for Einstein. We I mean, the redshift test was successfully concluded in this building in the 1950s, but they already knew they wanted to do it. It was very hard. They looked for shifts in the spectral lines of the sun, which is a wickedly difficult thing to see. I'm sure they can do it now, but that was not how it was done in this building. That's another story. So he was thinking about this, and in the midst of all of this fighting, he said, the closest solidarity between astronomy and the whole circle of exact science has been important to me. My interest has never been limited to the things beyond the moon. That was the classic Aristotelian distinction, things below the moon, which were corruptible and changeable, and things above the moon, which were perfect and unchangeable, but has followed the threads which spin themselves from there to our sublunar knowledge. I have often been untrue to the heavens. That is an impulse to the universal. So he's continued these interests in physics, astronomy, photography, measurement. He went up, he did balloon flights. He was... And in Alsace, he was in the midst of this fighting in 1915. As you know, trench warfare was no kind of fun. And he was in the battle of the roads, or the railroads that connected Mulhouse and Colmar. There were tens of thousands of casualties in those battles, and he was calculating and figuring right behind the front lines of what was there.
Is he in that picture?
No, these are just pictures on the Mulhouse-Colmar battle. This is from the Russian front. That's what it looks like. He also spent time on the Russian front, always a miserable place from Napoleon on forward to fight your wars. Not that there's a good place to fight a war. So Schwarzschild, on the 22nd of December 1915, so in the midst of, just at the beginning of winter, he wrote, Einstein and Schwarzschild were very good friends. And he wrote to Einstein, in order to become versed in your gravitation theory, I have been occupying myself more closely with the problem of Mercury's perihelion. I took my chances and made an attempt at a complete solution. So Einstein knew that the precession of Mercury was crucial, and it was, he said, the thing that gave him heart palpitations. He wrote to his mother when he got the right answer. I mean, he was very excited, and he really saw that as the clue to the validity of the theory. But Einstein was using approximations, and for the gravitational theory, the gravitational field, the geometrical field around a spherical object, and Schwarzschild solved it exactly. Sent it to Einstein from the front, and he said, as you see, the war is kindly disposed towards me, allowing me, despite fierce gunfire at a decidedly terrestrial distance, I mean, it was like right over the hill, to take this walk into this, your land of ideas. Einstein wrote back quite shortly after getting this solution, I have read your paper with the utmost interest. I had not expected that one could formulate the exact solution of the problem in such a simple way. So when we take it now to be obvious, this is, of course, the solution, the fundamental, most straightforward solution. I mean, compared to the complexities of care and other things that you've discussed, this was pretty straightforward. But Einstein didn't know how to do it. So he was really pleased, and he brought it to...
So he was literally in the trenches?
He was right, flying overhead.
With a pad of paper?
With a pad of paper, you know, calculating trajectories of the rockets they were launching and mortars, and then calculating the Schwarzschild solution right during it. How's that for a homework problem? So Schwarzschild then contracted by February. He was also in working on general relativity, finding a solution to Schwarzschild. His solution, on the verge of being killed by these, he contracted a deadly disease, and he had to go back home. This is in March of 1916, so right a few weeks after he got there, at his desk, and wrote a second paper. For the sun, he calculated the Schwarzschild radius is 3 kilometers, but died a few weeks after that, on 11th of May, 1916. It's tragic in many levels, but he was probably the person best outfitted to understand the mathematical physics of general relativity at this crucial moment. Now, this Schwarzschild radius became the subject of an immense debate that went on for 15 years. I mean, it continues long after that, but for 15 years, Einstein was in a kind of a panic about it, because it looked, and I'll tell you more about this in a moment, like there was a singularity. You've probably discussed the coordinate, but not physical singularity that exists at the horizon. But they were worried about it. And Einstein thought this was the end of his theory. This was a failure of his theory in a place where his theory should hold good, right? I mean, this is not some weird physical circumstance. This is a whole surface in space-time, and things look bad. So Eddington wrote and said, "There's a magic circle which no measurement can bring us inside. It is not unnatural that we should picture something obstructing our closer approach and say that a particle of matter is filling up the interior." So one idea was that you can't get inside it. There's just a physical obstacle that blocks you from entering into it. Yeah, firewall. A solid firewall. So in 1921, Max von Laue says that begins to look at what happens to light trajectories and began to calculate that. This becomes important, including for the shadow. Meanwhile, the political situation in Germany is deteriorating fast. This is the assassination just outside Grunewald in Berlin, which some of you will know very well. And there was an organization called the OC, or the Organization Council, and they were assassinating people right and left, internationalists, communists, Jews, everybody they didn't like. They had killed about 350 people by 1922. This is the assassination of Walter Rathenau, one of Einstein's good friends, a senior person in government. And he was invited to, so Einstein's invited to the Collège de France in Paris for the end of March, and he's very nervous about whether he should go. The French are not talking to the Germans after the war. There are lots of scientific conferences the French have canceled. The Solvay conferences, which we think of the height of international cooperation, were on the verge of failure at every moment because the French and their allies didn't want to talk to the Germans and their allies, and there were arguments about everything from seating to attendance. And Einstein was worried that the Germans would kill him, if he showed international solidarity. So he went back and forth about whether he should go. But he started lecturing on the 31st of March, 1922. Here's the crowd listening to his exposition of general relativity, special and then general relativity. Meanwhile, after the Eclipse expedition, which is November 1919, Einstein is instantly the most famous physicist in the world, and since Newton, and the most famous scientists certainly since Darwin. And so there's a film that's made about I just read, just before coming here, I looked it up again, and apparently there's a 30-minute segment of it that exists, which I'm going to try to get so we can look at it together. But most of the film has been destroyed. But it was a radical piece of filmmaking that used trick photography, special effects photography to get at various relativistic effects. So of course, I'm super curious about this. I also make films, so some of their story. I'll show you a clip of your resident hero here a little bit later. So Jacques Hadamard, the great mathematician, was there, and he says to Einstein on the 5th of April, so this is during his week at the Collège de France talk, could there be in nature stars so massive that the radial coordinate would be outside the star, and so the singularity, that is to say, I mean, I'm prejudicing the case by saying the coordinate singularity, but I mean the collapse of the metric in the form that they were all using in the sort of simple version of the Schwarzschild metric here would be outside the star, and so the singularity would occur in the metric equation in the physical world. So this is really putting the problem where it couldn't be stopped, right? I mean, as far as Einstein was concerned. Right now, it's like you can't have the whole thing filled up inside it. He's saying, well, what if you have a star that's actually squished together enough so that this is in free space and the metric itself blows up? So then, says Hadamard to Einstein, if so, then the metric is infinite and it makes no sense, or at least we should pursue its physical meaning. So now Einstein is really worried. Meanwhile, Painlevé, who's a minister in the government, leaves the ministerial offices to come to the Collège de France and is bothering Einstein about the twin paradox. But Einstein's not worried about the twin paradox. He's worried about this, because this is a threat to the very, as far as he's concerned, to the very existence of the, these are contemporary, this is Painlevé and Einstein. These are drawings that were made at the moment for the French newspapers. Einstein, then, the 5th of April 1922. This very profound question of Hadamard's is somewhat embarrassing. If this term could effectively become null somewhere in the universe, he calls it the catastrophe Hadamard, the Hadamard catastrophe, would be an unimaginable disaster for the theory. It's very difficult to say a priori what would occur physically because the Schwarzschild formula ceases to apply. So,
what does he mean by become null? The term could effectively become null.
The denominator of the term in the Schwarzschild metric in that coordinate system. So the whole thing becomes infinite. On the 6th of April 1922, the philosophers and the physicists gathered together, and Langevin says, he's the person who first called the twin paradox, he says, philosophy is no stranger to the development of general relativity. It is a philosophy that led Einstein to think that reality has no use for reference frames, that the laws of physics should be invariant under changes of coordinates. So they're talking about coordinate changes, and you would think, Einstein constantly repeating the refrain, physics is not the same thing as coordinate changes, that he would think about the coordinate changes that might rescue you from the Hadamard catastrophe. Becquerel says the coordinates that Schwarzschild uses are those with which, for a physicist, the universe becomes most intuitive. So they're all like locked into this coordinate system, and in part because I think Einstein is still in the thrall of the particular form that he received from Schwarzschild back during the war. Becquerel says, Einstein says, one can always choose that representation that one wants if one believes it will be the most convenient for the work at hand, but that does not have an objective meaning. Objective meaning for him is something that's coordinate independent. But nonetheless, he's completely worried about this. And he starts to wonder whether stars of such a massive size could not exist. He's floundering around, trying to think of a reason why physically you could never get this collapse. Einstein did not want his theory to depend on any particular matter of a particular model of what matter existed in order to escape from this misfortune. He wants to be independent of the misery that would be engendered by the Hadamard catastrophe. Einstein, perhaps the pressure at the center of this collapse becomes infinite, stopping the clocks, stopping time, before the star can become massive enough to produce a Schwarzschild radius outside its body. That is all I can say, he says, since I do not wish to make hypotheses. Des hypothèses je ne veux pas faire, je ne peux pas en faire. And that's, of course, a reference to Newton, who says, hypothesis, I'm not going to make hypotheses, who's attacking Descartes, who's got all these models of the universe, and Newton says, I don't want to talk about your stupid Cartesian models. He doesn't say that. But he says, he wants his 1 over r squared model, and he doesn't want to get into the details of how these little particles of matter, little, medium, and big, interact with each other to make these vortices, which Descartes wanted to use to explain what gravity was. So Einstein's unnerved because all he can think of is making some kind of model that will stop the collapse, but he hates the idea that the theory would depend on a theory of matter, that the theory of general relativity will depend on an account of matter. So this goes on. Even in 1949, Whittaker says every gravitating particle has a ring fence around it which no other body can penetrate. And this ring fence is sort of a callback to this picket fence that exists, sort of that keeps you from getting inside the boundary.
It's hard to listen to all this and not conclude that they didn't understand what coordinate invariance. Because nobody's asking, is there a coordinate system in which it...
Right. So they not nobody. By 1931, 32, 33, they start to ask about it. Why does it take so long? That I think is a perfectly good question. I think they were attached to I think Einstein was charmed by the Schwarzschild solution that he got. And I think it kind of froze their attention. And because I gave you those quotes about reality and objectivity sort of existed only for those physical effects that were independent of coordinate changes. So he was saying that, and then 10 minutes later saying, there's this giant problem with the Schwarzschild metric in this coordinate system. Yeah.
One would think that like a natural thing to do is look at geodesics or look at like some scalar that you can make out of curvature tensors. Like,
yeah.
And just nobody did this.
No, well, von Laue starts to draw these trajectories, and Hilbert. So you'd think that.
It clearly shows you like a finite affine parameter reached a like.
Okay, I mean, I'm not. There are two contradictory things that they believe. One is that you can change the coordinate system. That's the whole point of general relativity, right? That's why he extended it. And he's fixated on this particular coordinate system, which is leading to the catastrophe that makes him think his whole theory is going to be blowing up. So that's interesting, right? But it's I don't know. I mean, I can't reconcile those. But by the early 1930s, his friend Einstein's another one of Einstein's friends, Georges Lemaitre, who's a priest in Belgium, says says, look, there's a simple coordinate change, and that makes the metric at r equals 2m manifestly regular. The metric doesn't blow up. Einstein's saved. The theory is good. Everything's happy, right? But it was a decade of floundering in this uncertainty about what was going on. This is Einstein and Lemaitre. So things continue in the 30s. And Oppenheimer gets interested in this. And it's probably the most important physics. I mean, Oppenheimer, of course, is famous. He led the Manhattan Project. He was, destroyed in every possible way by McCarthy in the April 1954 hearings on the hydrogen bomb, where he was accused by the right wing of having slowed down the American development of thermonuclear weapons. But during the late 30s, when he was head of the first head of the Institute for Advanced Study in Princeton, he got very interested in this. And with his student Snyder and others, they began to actually try to make a model of what would happen to put in equations of state and actually look at stars and say, what if they were, you got a pretty big star and they start to collapse, and could this, what would happen? And, they convinced themselves using the calculational methods that they had. This is sort of pre-World War II, Marchand calculators, big crank and gears, and they convinced themselves that you could actually get this effect. This is 1939. So September 1st, 2nd, 1939, the Nazis invade Poland and World War I begins in earnest. And it's, it's a world catastrophe, and Oppenheimer's swept up in the effort to start planning for nuclear weapons. They think that the Germans have Hahn and Heisenberg, and I mean, they still have a lot of very good physicists there, and the Germans have been buying up uranium mines in the Belgian Congo, and so there's a real worry. They go to Einstein signs a letter written by Teller and signed by others, and it goes to President Roosevelt. The Manhattan Project gets underway. I once was asked at Hawking's 75th birthday, I was talking to him, and I asked him about some of this, and he said he wrote a message out in his careful and necessarily labored way, and he said, Oppenheimer really invented black holes. Too bad about the bomb. So in 1939, a month after Robert Oppenheimer and Snyder did some of these collapse calculations, he supposes, there's no evidence that Einstein really paid attention to what Oppenheimer was doing. They didn't like each other. Einstein was the first and most famous member of the Institute. But I think Oppenheimer thought Einstein had disconnected from the important issues of contemporary physics, and I think Einstein thought Oppenheimer was kind of an operator and didn't like his politics and his footsie with the state and so on. So anyway, they suppose that gravitating particles constituting the star have intrinsic motions that prevent collapse. It'd be very interesting to have overheard a conversation where Oppenheimer is arguing you actually can get this thing that Einstein's theory predicts, and Einstein's saying, well, no, there's some kind of theory of matter that's going to prevent that from happening. And Einstein said the Schwarzschild singularity does not appear for this reason that matter can be concentrated arbitrarily. So after the war, there's just make sure. After the war, the black holes are really shunted aside. All of general relativity really becomes the playground for mathematicians at the Institute for Advanced Study and elsewhere. And neither Oppenheimer nor Einstein's attracting people to this as a major area of study. Einstein continues working on aspects of general relativity, of course, but it gets shunted aside because after the war you have nuclear physics, you have the new order of things in the world, the beginnings of the Cold War, which start really in earnest by 1947. World crises. Einstein gets involved in anti-racism efforts. There's a lot going on, and physics has as its center weight things like mesons and the nuclear forces, and is there a simple form that could have? People trying to extend quantum electrodynamics without much success. Arguments about whether quantum field theory even is a reasonable thing to be working on, whether there are alternative approaches. And it's Wheeler, who's here, John Wheeler, comes out of the war. He was Feynman's teacher in the pre-war period, and Feynman, of course, goes off to work on the atomic bomb in the theory group under Beta in Los Alamos. And Wheeler works on the bomb too, supervising reactor construction. And Wheeler comes out of the war with enormous respect for engineers and engineering and large-scale state-funded projects. He's far more conservative politically than some of the others, allied with people like Lawrence and Alvarez, Teller, and against people like Beta, Oppenheimer. Fermi's a kind of switcheroo figure in this period. And there are arguments about the hydrogen bomb. And they, before the war, just the beginning of the war in 1939, 40, 41, the physicists thought that the atomic bomb was so easy, the uranium-235 bomb, that they assigned it to Robert Serber, a young physicist there, and they say, you do that. The grown-ups here are going to work on the thermonuclear bomb. That's much more interesting. And so at first, all of them, Beta, Teller, Oppenheimer, these already very famous physicists wanted to think about the hydrogen bomb. But then during the war, it turned out it was more complicated to make an atomic bomb than they had anticipated, and the only one who refused to work on it was Teller. So Beta said, okay, Teller, you go work on the hydrogen bomb. She didn't really get anywhere on during the war, but then after the Russians detonated a bomb in 1949, in the summer of 49, it became a huge debate and split the physics community. Wheeler was very much at the center of that, and at the Institute for Advanced Study set up a group to, I don't know if you know Princeton, but there's this failure of a shopping center that was supposed to be a huge success like Stanford's, but Route 1 in northern New Jersey is not, Palo Alto. Never worked. But that area had been used by the military and to do various things, poison sheep and do really exciting things like that. But anyway, in this period, Wheeler had ran a computational group. Yeah?
Do you know anything about, were there spies at the IAS? Because, these physicists were building bombs for the U.S., so were the IAS infiltrated?
That's a good question. I don't know the answer to whether there were there were lots of spies. I don't know if there were any at the IAS.
Were any of these physicists spies?
Were there any physicist spies?
Yeah.
Yeah. That will tell you that. That's another story. There were spies in Canada, Chalk River. There was a lot of spies. Spies everywhere. So Wheeler.
He was at the institute, not the university?
No, he's probably at the university. So they set up a computation group. Ken Ford was one of his students, and they did these calculations on implosion. these implosion ideas that had first developed by Teller, and von Neumann had contributed some of the new supersonic compression theory of making lensed compression to get the plutonium bomb to work. But all those ideas became important around stellar collapse and some of these things, but they were first in the hydrogen bomb. And Wheeler was always fascinated by the conversion of matter into energy and became riveted by the hydrogen bomb problem, worked hard on it, and they did simulations that showed that a new configuration that became famous as the Teller-Ulam configuration could work. And Oppenheimer actually changed his mind about the hydrogen bomb based on those simulations that were done at the IAS, because they showed that this thing probably would work. Teller had a completely different idea about how to make a hydrogen bomb during the war. Back to the main point. So Wheeler worked on the hydrogen bomb and on various forms of matter to energy conversion, and he wrote about that. He thought that was a central feature of what would emerge in particle physics and elementary particle physics. And in the mid-60s, or maybe early 60s, Wheeler opened a notebook and said, I'm going to learn about general relativity and stellar collapse. And he started thinking about these questions. And Wheeler really is the person who sort of spearheaded. He was the one who taught all that next generation, Kip Thorne, all the famous relativists, or not all of them, but many of them, at least in the United States, came out of that. And the fall of 67, in this building, which is a Goddard NASA Center in Upper Broadway, in the fall of 67, he was giving a lecture, and it was an exchange with people in the audience, and that's when the term black hole was coined. Black hole the term became something of a scandal, and Wheeler doubled down by saying all you could say about a black hole was its mass, its charge, and its spin, and he called this conjecture, of course, a black hole has no hair. Wheeler said, Feynman called my language obscene when I tried to summarize the remarkable simplicity of a black hole by saying a black hole has no hair. I guess Dick Feynman and I had different images in mind. I was thinking of a room full of bald-petted people who were hard to identify individually because they showed no differences in hair length, style, or color. The black hole only has three characteristics: its mass, its electric charge, and its angular momentum.
Density. One can't predict the future. This implies something strange could happen when the Earth star collapsed. We wouldn't be affected by the breakdown of prediction if the singularities are not naked. That is, they are not shielded from the outside. When John Wheeler introduced the term black hole in 1967, it replaced the earlier name frozen star. Wheeler's coinage emphasized that the remnants of collapsed stars are of interest in their own right, independently of how they were formed. The new name caught on quickly. It suggested something dark and mysterious, but the French, being French, saw a more risky meaning. For years, they resisted the name, true nor, claiming it was obscene.
And then Thorne joined in this and said the French translation of a black hole has no hair is so obscene that French publishers resisted it vigorously to no avail. Penrose introduced the cosmic censorship idea, building on this notion. The singularities, he said, are outside space-time and challenge the very possibility of law-like behavior. They block the prediction of the future from the present. Penrose conjectured all naked singularities are protected by censorship, a horizon. So it's actually sort of funny to follow this. I don't remember whether I kept the slides in later, but the French didn't see themselves as bothered by this at all. They said the problem was the Russians. And the Russians found it so obscene that they wouldn't use the word. The Russians said they had no problem with it. Anyway, so in 1970, so shortly after the naming of the black hole and some of this important work by Penrose and others, there was the astronomers, cosmic ray physicists, joined forces to make a satellite, the Uhuru satellite, that was going to measure X-ray sources in the sky, launched on one of these new and fairly cheap rockets. This is Bruno Rossi on the right, I don't know, and Marjorie Townsend on the left, and fixing up the satellite on its way to the launch pad. Another view of the satellite. And here it is aboard a Scout B rocket, which launched on the 12th of December of 1970, and started seeing these pulses of X-rays. And they were able to localize those to Cygnus, the swan, in that constellation, and began to reason about it. And it turned out they could show. You talked about Cygnus X1 and binary. So what they saw was a visible star that was clearly rotating, because they could see its Doppler shift spectrum. They could figure out its mass, its star type and its mass, and they could figure out that they could see that they could not see its partner that was causing this rotation in this binary motion. So there was something not seen, and that you could calculate the mass of by the motion of this visible star that you could understand quite well. So then this X-ray data comes in the months after December 1970, and they begin to be able to say what the radius of this is by the pulses, by sort of a hot spot going around, some kind of plasma junk that going around the unseen partner. So you've got material from the visible star that's falling around the invisible star, and you can calculate what the biggest circumference that it could have. You can't go faster than the speed of light, and how much mass it has by the motion of the visible star. And so they began by the early 70s to say they'd seen a black hole. That was the first big sort of reality test for stellar mass black holes. And it was that period, that in the 1970s, over the whole of the 1970s, that caused a kind of rift among physicists of whether was this sufficient evidence for the existence of stellar mass black holes, and that other such binaries were found with an unseen partner, a visible star orbiting around an unseen partner, look at the X-rays, figure out what its maximum size could be, and that maximum size, given the mass, made it a black hole. So that was the argument. And if I was dividing up the sort of reality arguments for black holes, I would have start from that period around Schwarzschild up through Lemaitre, sort of 1916, 1930, then late 1930s with Oppenheimer actually trying to model this with equations of state and the collapse, and then this revival of general relativity culminating in this X-ray, this unexpected. They weren't looking for binary stars, but they weren't looking for stellar mass black holes, but that became a big argument for the physical reality of black holes then. But it was by no means a consensus view. And then there are another round of movies that begin.
Is it a majority view?
I can't say. I know. I don't want to put it on tape, but I can tell you some of what I remember from people saying in the 70s. Here. Yeah.
So it wasn't Kruskal second who understood that there is no really physical singularity, right? It was Lamarck, you're saying?
Yeah, I think it's before Kruskal. I mean, so.
But by the time Kruskal found coordinates, everybody was already agreed
That the horizon was not singular? Is that your question? Yeah, I think so. I don't think that was much debate. I mean, once people saw that it was a coordinate problem, not a physics problem, I think that became pretty much accepted. And then attention shifted to the singularity. To the singularity that we know and love or don't love at the center. But Einstein he just never liked the black holes. He fought them sort of every step of the way. He wasn't even that happy with gravitational waves, although I think he was more accepting of those than of black holes.
Did they know it was a null surface?
I don't know when that language of null surfaces. Do you know when people started talking about that?
You know, I thought it was like the idea that it was that you could cross it going in, but not coming out. Right? That it was a one-way membrane. Wasn't that Finkelstein around the time of? I don't know.
I don't know.
Yeah.
So people started making movies, and what's interesting, if you do, I'm not going to make you suffer through too much of this, but there were movies. Periodically, there are these movies about black holes, up through in fictional movies, up through Interstellar, and what you can see them as a kind of a probe of what the anxiety of the period is. So there's a black hole movie where black holes are sucking all the energy from the electrical system right at the moment that the oil embargo hits. Then after 2001, they become sort of a symbol of terrorism. So you can sort of look at black holes as a way of the Rorschach of physics. So there's a Disney one in 1979 that made the physicists and astronomers crazy because it's terrible physics. Here's the one that I was talking about before. So it was called the French immediately translated. It was a popular Disney movie in France, and it was called Le Trou Noir. So they didn't think it was so obscene that they couldn't market it quite well. And they say the film 1979 had to change its title on the territory of the Soviet Union because the term black hole was such an obscene term, absolutely incompatible with a resolutely familial film. So this is the French talking about the Russians. So here's the Disney film which came out the same year. In Russia, it says black hole. So it was Cherny Dira. So that was not such a problem. I'll show you just a brief clip of this. How can I resist? Time.
There is an inexorable force in the cosmos where time and space converge. A place beyond man's vision, but not his reach. It is the most mysterious and awesome point in the universe. Where the here and now may be forever.
My ship, you ask.
It is unavoidable. Moving through space, swallowing everything in its path. Radio waves, light,
Are you programmed to speak?
even planets and stars.
Fire thrusters.
That madman is headed straight for the black hole. What'll we do?
We wait.
But science fiction and black hole physics have never been that far apart. And in the mid-'80s, Carl Sagan and Kip Thorne are the friends, and Sagan sends Thorne a book manuscript that becomes eventually the film Contact, and asks Kip Thorne to correct the physics. And Kip Thorne says, well, you can't really have black holes making kind of a subway system among universes, but we could make wormholes. And so he rewrites pieces of the manuscript, which Carl Sagan was having trouble getting published. And then after this exchange with Carl Sagan, Kip Thorne begins to wonder, well, could you make wormholes? What would it take what kind of states of matter and negative energy and various things to hold a wormhole open to get a kind of rocket to go through it, or a person in a pod to go through it? And he starts asking this question that he considers a kind of cross between fiction and physics, or a kind of engineering attitude towards gravitational theory, asking the question, compatible with the laws of physics, if you had infinite resources at your disposal and infinite time and an infinitely sophisticated population, what could you make? And what kind of effects could you make? And this actually caught on. Malcolm Perry wrote papers along these lines, and Stephen Hawking was interested in that. And
we had a lecture from Moldacina earlier in the course about wormholes.
Yeah. So this idea of so this is really at the edge of sort of an engineering attitude, a science fiction stance, and physical law. So Thorne says a physics, he was interested in a physics more like science fiction. He and others, including Hawking, began publishing about engineered space-time on time machines and wormholes, potential paradoxes, and their resolutions. Hawking talked in 1992, I love this phrase, the Chronology Protection Agency, to, quote, make the world safe for historians, so that you couldn't change the past in such a way that my job would be even harder than it is now. Now, a second epoch in the push towards the reality of black holes comes as people begin to think about not stellar mass black holes, but about supermassive black holes. You've heard a lot about that here. And Andrea Getz, from really the beginning of her career, got interested in using optical telescopes to probe this is a picture from 2006, but long before that she'd gotten interested in this. She's still interested in this at UCLA. She has a whole center that looks at this. And she wanted to look at our galactic center at Sagittarius A star, which was the original target for the Event Horizon Telescope. That's what all of us thought we were going to look at. And then there's this other galaxy, M87 in Virgo, called Messier 87, M87, after the 18th century French astronomer. And that's one of the biggest galaxies that we know of, and it's got correspondingly the biggest black hole, which is billions of solar masses. But the one in our galactic center is much quieter. It's less going on around it, but it's small. And because it's small, the light crossing time is shorter, and things happen really quickly. And that makes it much harder to image, and we eventually had to push it aside. But on the sky, it's about the same size, like the moon and the sun are about the same size with respect to us in angular size. But even though one's obviously much bigger than the other. So, we've talked about dogs' ears being like 7 human years, and so a minute on Sagittarius A star is like a day on M87. So light, everything that orbits around it, a hot spot or changes in the aspects of the accretion disk or the funnel that's the beginning of a jet, everything is slowed down when you're billions of solar masses as opposed to millions of solar masses. Our puny supermassive black hole at the center of our galaxy is about 4 million solar masses, and M87's black hole is about 6.5 billion solar masses, but it's correspondingly farther away, so it looks about the same size. So already looking in early days using adaptive optics, where you take atmospheric interference and you correct the optics. This is all in the optical. The amazing thing that they do, that Andrea Getz and the corresponding group that's in Munich, is that they're looking through optical telescopes at something 26,000 light years away. It's amazing, really. And they began to look at this cluster of stars at the center of the galaxy. Sagittarius A star, by the way, has nothing to do with, you probably don't know all this, but it's nothing to do with stars. It's Sagittarius A and an asterisk, and that's modeled on a twin metaphor to nuclear physics, where you can if you have an excited nucleus, it can collapse back to its ground state and emit a gamma ray. I mean, so those are designated with an asterisk and pronounced star. But it's got nothing to do with like the sun or a star like that. It's a star like an asterisk modeling the nucleus of a galaxy on the nucleus of an atom, which itself is a metaphor from the nucleus of a cell. So it's like this migrating metaphor that just keeps going, and nobody remembers what it's for or why it's called that. But that's what actually it corresponds to. So at Sagittarius A star is this one at the center of the Milky Way. And here's a, having studied this for really the whole of her her career, Getz begins to see, you can see this, the motion of these stars. You see the years ticking off there. So she begins in the 1990s and continues up to the present. This only goes through 2010, but you can actually begin to see these orbits of these stars, which is amazing. I mean, to see a star hauled around in sort of planetary time around this black hole is amazing. I mean, the gravitational force needed to treat stars like, Mars or the Earth or Jupiter. It's amazing. So, and then of course, in a way, the next big change is with LIGO in 2015, where they begin to look at gravitational waves. And through the calculated, for the use of numerical general relativity, they can make patterns about what they would expect two black holes merging to look like. And I remember when I first heard about this search, it seemed to me like, it made me wonder the way I've often wondered when these armies in the Middle Ages in Europe fought each other. It's like, how the hell did they find each other? I mean, there's no radio, there's no newspaper, there's nothing. It's like, it seems like you could wander, you spend your whole life looking for your enemy and not finding them. So I mean, how do these black holes are all of space, and they come and they bump into each other? It's like the story of the two cars in North Dakota that crashed when there were only two cars in North Dakota. So they made these models, these templates, and as you know, they got this amazing coincidence, not only with the template, but with maximally separated laboratories in Louisiana and Washington State. Originally, it was going to be in Maine and the Southwest. I mean, you want it to be as far apart as possible. So the blueberry farmers in Maine got really mad at them, and there's a big fight about that. And then, anyway, it ended up in Louisiana and Washington. So there you had, the Getz and the UCLA and the Munich groups had something visual, optical, but they were far away. They were sort of 1,500 Schwarzschild radii out. I mean, not far, amazing, but far compared to maximally strong general relativity at the horizon. And then the LIGO got close in. They could see this in spiral, and then the ring down as these things merged and settled into a combined black hole. But that was very close in, but not with an image. So in a way, the Event Horizon Telescope is trying to join the optical visual side that is not too close, and the close-in amazing experiment of LIGO that opens up a whole new register of astronomy. I mean, it's an astonishing thing. Oh, here's the Munich group's beautiful European Southern Observatory model of the same thing I showed you, but goes up farther towards the present. And you can see the stars doing their beautiful Keplerian ellipses around the unseen Sagittarius A star. And we've now been able to see it go around a couple of times, which is amazing. So the Event Horizon Telescope is and was an attempt to do very long baseline interferometry, as you heard from Shep, no doubt, and creates this immense amount of data, petabytes of data, 4 or 5 petabytes of data in the observation run of April 2017, which is the data that were used for the recent release on April 10th of this month. And the procedure was to try to take these image processing. I apologize, I don't know exactly what you've heard about, so forgive me if this repeats a little bit what you've done. Did Shep lecture after April 10th or before April 10th?
Before.
Okay, all right, so I won't, yeah.
Yeah.
So the idea was you have this sparse, noisy image. It's noisy for various reasons. Sagittarius A star is noisy because things are changing right there. M87, not so noisy at the source. There's noise that's introduced by coming to us through the plane of the galaxy from Sag A star, and there's, so you want to use a very, to get maximum resolution, you want a small wavelength, and about 1 millimeter turns out to be a triply good coincidence. First, it's near the peak of the billion degree Kelvin excited plasma that is orbiting around hanging around near the horizon. Second, it's really good at penetrating the interstellar media, and so it becomes the jet and all those sorts of things are optically thin in the millimeter. And third, it gets through the atmosphere, kind of. It's in a pretty good place in the absorption spectra of the atmosphere. So you have these, and it's also it's the limit of what the electronics can do. So, and now it's 1.3 millimeters is actually what these observations, the famous picture, were done at. And the next generation, which is being set up now at 345 gigahertz, is 0.8 millimeters. So it's a 50%. I mean, it's a big drop down, and that'll give a big increase in the ability to resolve images. And then you need the big dish. That's why you connect these 6 sites with 8 antennae around the globe, and adding Greenland, other ones that we're going to add in the next round. And then you have this image which can be filled in somewhat by the fact that the Earth is turning, so that the baseline facing the black hole is changing, and so you pick out different frequencies and you fill out the image, but it's still sparse. It's like taking shards of a mirror to make one big mirror, but you're missing big chunks. And then if you were able to rotate these shards, you could fill in more, but you'd still have big holes in what you saw of the image if you were just in the XY plane. So it's noisy and sparse. So then the question says, well, what kind of image could you get from that? Well, you need to just ask the question, what kind of image is compatible with that sparse, noisy data, is a poorly defined problem. It's like saying, here are a bunch of points, draw the best line through it. You have to say, what kind of line? You want a straight line? Do you want a section of a circle? What kind of line? What prior assumptions do you make? And that sort of Bayesian approach is a big part of what the project was working on. And then the question was, does it work? So we made synthetic data like these, either real astronomical images or blurred astronomical images or geometrical images or blurred, and just said, if we use our imaging technique, we take the image that we made, blur it, make it noisy, and then see if you can capture that with your image making program. I mean, the problem in some ways is like saying, test this camera with a new kind of film on an object that you've never seen. I mean, that's not the way you would test your system, right? Normally you would take a lens, put it on an understood camera body with CCD or films that you understood, and point it at a test chart and see how it does. Then when you knew the lens worked, you could try a new camera body with a new CCD system and a new set of protocols for how the CCD dealt with the data, which is actually quite a complicated affair. and try it on a test chart. Then with a body and a camera and a lens that you knew and trusted worked on a synthetic target, you could then point it at something you'd never seen before. But that really had to be worked out in this case. And that's what a lot of these last years have been doing, was trying to say, does the lens, all these antennae around the world, do they produce a reliable image? Do the algorithmic programs that get you, that make certain assumptions and produce an image, able to do that on a known target like these? And then maybe try something out in space, take a look at a known quasar or something like that, and see if that works. And then if that works, then point it at the candidate black hole. But that's a big part of the argument. So here's some examples of the synthetic images. You take random images off of the internet, or simulated black holes or other things, and you would try all these different image making programs and try to see what did well and what begins to degrade.
Observers can speak with philosophers and mathematicians, and unforeseen connections can be discovered and ignited and built. The Event Horizon Telescope is a new instrument that we're assembling with a global team. We want to take the first picture of a black hole.
This is in Mexico.
We take many radio telescopes around the Earth
What
and we
I heard
link them
yesterday,
together.
the total power was working, the gun was locked, noise temperature was excellent.
Okay, but if we went back to this old gun, we're still compatible with the...
We have a goal of seeing something that struggles with all of its might to be unseen. And we're pushing the technology as far as we can go.
So this is the,
Observers can speak with philosophers and mathematicians.
So this is still less than 0.03, this is 0.04.
this is debating weather in April of 2017. You have to get good
We
weather
just
all
said
over
this
the Earth.
Okay, good.
I think it's going to be amazing for all of us to be able to see a black
I
hole.
mean, based on what we saw a few hours ago, the weather is good.
But beyond that, there is a very definitive prediction of general relativity in terms of what shape and size the hole and the ring around that hole should be.
What if Einstein is wrong? Then the light bending around a black hole could be much different. The existence of an event horizon, indeed, may be called into question.
I basically think that we should trigger for tonight. Probably the best weather we're going to get. Technical issues are breaking our way.
Yep.
So let it be written, so let it be done. I will make a decision. I will broadcast it.
Track D is a go.
And then, all around the world, all the telescopes will swivel at the same time, and we will begin to record photons from the black hole.
So then there's the theoretical work that Andy and Malcolm Perry and Sasha Heiko and Stephen Hawking have been doing about, you've probably done a lot already on entropy and software.
Maybe next semester.
Okay. All right. So one of the issues, so you're going to hear a lot from Andy about this. You're lucky. He's a great contributor to this problem. But one of the issues has been that there's been a kind of a rift in how people think about black holes from the point of view of those who came up through quantum physics, quantum field theory, and that way, where the idea that if you know the present, you can predict the future. Even quantum mechanics, you think, oh, well, that's got uncertainty in it. But the equations of state, the state vectors of quantum mechanics are known at the present. You can say what they're like in the future or the past. The Schrödinger equation or the Dirac equation or all of our physics has that feature. And people in particle physics or related areas grow up with this unitarity assumption as built into the fabric of what they understand physics should be like. But general relativists don't. And people that came out of the long tradition of general relativity, great relativists like Wald and others, have always sort of said, well, why should we assume that we can predict the future from the present uniquely? I mean, that maybe not. And so if you look at black holes now and you believe the mantra that was introduced by Wheeler, the black hole has no hair, then you can't tell whether the black hole was made out of giraffes or school desks or anything else, right? Or stars, or it could be any, or dust. You don't know. You can't look at M87 and say that was made out of dust or civilizations or stars or other black holes. It's gone. And so, but we know that quantum mechanics and relativity can't exist in an incompatible way. That would just be terrible. And as you go closer to the singularity, the center of a black hole, you know, the scales call quantum mechanics into existence. You can't avoid that. So something has to give here. And so one of the questions that was raised by a great paradox of modern physics that was raised by Hawking in '74 was that quantum mechanics essentially and general relativity seem to be in different tracks, that you would have in black holes a way of annihilating the past, of making it impossible to say how things were in a region of space and time. You couldn't say how it was made, and correspondingly wouldn't be able to predict the future. So Hawking reasoned at the boundary between quantum mechanics and black holes and began to think with others like Bekenstein about how to think about black holes as having an intrinsic entropy, of having something, the temperature and entropy, to be thermodynamic objects in a very deep way. And so the question was, could you calculate that? Could you figure out what, from microphysics, what that was? And Andy and Kumran-Vafa did a remarkable calculation in string theory and about trying to calculate that entropy and get successfully reproducing what Hawking said should be there. But there was the question of, then do you believe that string theory is solid? And so the question then that Andy and Perry and Hawking and Sasha Heiko worked on was, without assuming the details of string theory, could you get to this? And they called this soft hair. It's a little ridiculous, I'm telling you this, but Exhibit A is over here. But so they began to work on this, and over the last couple of years, the long calculation, I'll show you one. I'm not going to go through this whole thing if you're going to do it next semester and get it from the horse's mouth. But here's a moment in this calculation where Andy, this is shortly after Stephen Hawking died, and the calculation wasn't going so well.
Theta tilde y, and this contains an epsilon double prime, that contains an epsilon prime.
So that would go like 1 over W plus.
So this goes to like 1 over W plus, which means you've got to compute this thing to W plus. But you sure there's not something else?
No, it doesn't. No, it doesn't, because it's only the 1 over W plus term that can contribute.
Right.
We need that 1 over W plus.
So you have to compute this toward a W plus.
No. No.
Oh, right. Okay.
Because the range of W plus is 0, so if we don't have 1 over W plus there, we get 0. We didn't understand this in Red Sun.
Oh yes, we did not understand that. But we thought in Brinstock that things were relatively simple. You didn't have to think about so much. But since then we've discovered all kinds of other things which do contribute and complicate matters.
In Britsop we thought we could do it by hand. 10 pages. Turns out to be among the most that's done.
1,050 terms.
1,050 terms. You cannot add 1,050 terms without making a single mistake. Or I can.
So things got better with this calculation and came to a happy conclusion, and was published, I don't know, 7, 8 months ago, something like that. So, but part of understanding the reality of black holes is to be able to make sense of this, the thermodynamic nature, to have a microscopic account, not just a macroscopic account of what black holes are, what this surface of no return is, what this boundary, this Schwarzschild radius, Schwarzschild surface is. And so that continues to be a real question. So in the Event Horizon Telescope, we're trying to get close to that surface, to keep getting, keep moving in closer and closer to the Schwarzschild radius. And these kinds of synthetic images, there are the old techniques that the astronomers have been using. One of them is called clean, where you have this fragmentary picture of the sky from all these far scattered 6 sites, 8 telescopes, or you increase that, and they look at a target of what they think, what they're interested in. Astronomers are basically interested in point sources like stars, or some unresolvable quasar or something like that. And so if you were looking at that, you would say, okay, well, what does a point source look like with this fragmented camera of the very large baseline? And so you look at the image, the point source, and what does the image of that look like? And you see a lump of brightness at the middle, and then you see all this junk around it. So you know that a point gets mapped by this fragmentary telescope, by this sparse data, into this mess. So now you look at the image that you get, what's called the dirty image from the sky, and you see a bright spot, and you say, okay, but I know that in addition to this bright spot, there's all this other crap that's around it that I should subtract out. So you take some of that brightness and use the pattern of the point source to subtract it out. And that removes some of these flanges around the bright spot, and you clean up the image in this way. But it can lead to all sorts, there's certain problems with this. One of the problems is it's not very good for extended sources. So if you had a disk and you did this to a lot of the points, you could actually eat away and create holes in the brightness. And that's a nightmare, right? The worst thing that could happen would be that in imaging something that didn't have a hole in the middle of it, we made a hole in the middle of it by our method. So years ago, I wrote a book with Rain Daston called Objectivity, about images in science and the quest for objectivity. And we wrote that these strategies of making images were always born of fear of something, fear of somebody imposing their will, or fear of an instrument artifact, or fear of something else. But this time, I really felt it as a fear, like keep me up at night fear. Because if one of these methods we've seen famous experiments like BICEP 2 and others where they thought they saw something, and then you looked at it more closely and it went away. And I wrote the first book, my PhD thesis, it was in history of science before I did the physics, was called How Experiments End. The whole book is about how theoretical presuppositions can lead experimenters to find things that they expect to find. So I was very paranoid about this, but not just me. All the other 206 people on the collaboration were really worried about that. And so from June to anyway, I'll come back to that in a second. So there are 2 methods. There are the traditional astronomical methods, these clean methods, and then these regularized maximum likelihood methods, which are these Bayesian techniques, where you assume something, like how distributed it is or how sharp the edges are, or there are various things you sort of can tune, and then there's a cost function which is minimized, and you get the image, the best image you can do. Yeah.
But is it completely bulletproof now? I mean, BICEP 2, they also were very careful.
They weren't. They scraped off of a PowerPoint slide the results from the Planck experiment to get the estimate of the amount of dust. And Planck wouldn't talk to them. I mean, the Planck experiment wouldn't talk to them.
Is it impossible for the people doing the calculation themselves to know whether they're doing something bulletproof? Doing the experiment themselves?
Okay, so one of the things that they did was to take we did, I'm not going to blame them, but was to divide the image making group. So there's a sort of an arc of all the instrument group, and they have there's 6 papers paper 1 is, well, paper 1 is an abstract. Paper 2 is the instrument. Then paper 3 was cleaning up the data, called, making sure that the data wasn't corrupted. For instance, one telescope was not good at pointing straight up, and so when it got near the top, astronomers have names for this, I don't know them, but when it gets near the top, it slewed, and so that led to some strangeness in the data. So you had to go back and look in the log books and check. I mean, there's a lot. So corrections and errors. This was paper number 2, paper number 3. Paper number 4 is making the image. Paper number 5 are all the general relativistic magnetohydrodynamic, the plasma physics simulations, and which you need to be able to, all this shadow is the shadow made by all this hot plasma. So understanding the hot plasma is it's a big turbulent mess. So you have to model that, and their magnetic fields and their jets, which are caused by these helical magnetic fields that come out of the poles, and it's complicated. And then paper 6 was theory and sort of trying to say, well, what could you say? Could it be other things? Could it be a gravis star? Could it be a boson star? Could it be, all these sort of, saying, well, what would it be if it was something other than a black hole, and would we be able to tell? So in the image group, we divided into 4 groups that didn't talk to each other. So whenever we would have a discussion, we'd put up non-transparent, translucent but non-transparent paper. This is one of the grad students sealing off the room so nobody could see inside. This is within the collaboration, but so you couldn't be sure that the you couldn't be sure, but there were the old astronomical methods. There were 2 groups that didn't talk to each other using clean, and 2 groups using these regularized maximum likelihood methods, the Bayesian methods, and they weren't talking to each other. And so you had 4 groups. You could say, well, they're not completely independent. We all swim in the same sea, so to speak, but nobody knew what the other ones were seeing. This is in one of the groups, group 1, that was doing regularized maximum likelihood.
Shut, close the door. Okay, we ready?
Wait, what is happening?
We're trying to make an image right now.
Can we just case things a little bit?
Well, no, first of all.
When we
So you have, they began to see the image. This is in June. And then in July, we took these 4 images and presented them together. This is July 24th. And the RML is regularized maximum likelihood. So those are the 2 groups, team 1 and team 2. And the 2 clean groups, the traditional and well-established astronomical techniques. And we were all getting a 40 or so microarc second shadow with a ring, all getting brightness basically in the southern part. And so that gave us a lot of faith that we were looking at something real, that these 4 expert, each of them using whatever techniques they could, and in this case, this is an average image on July 24th, and this is looking at M87. And then another thing that you began to see, so then the question was, well, if people are using their best judgment about how to adjust these parameters, what if they were tuning the parameters just the right way that they were getting this? And that for the regularized maximum likelihood. And in the clean method, which depends on a lot of expertise, how much do you subtract, and what order do you subtract, and how do you apply this you get rid of the this dirty beam in different parts of the image. What if we somehow, even though we were not talking to each other, each of the subgroups was using their expertise too much? So then the question was, could you use a kind of mechanical or algorithmic procedure to explore this big 6-dimensional parameter space of all the different settings, how sharp the boundaries would be, how compact the the illumination would be, there are these various things that basically go into the cost function of the image, and you try to minimize that. So we took that and took. Oops, I guess I don't have pictures of that. So what we did was to then take synthetic data and to take this complicated parameter space, sample from all over it, and then use the computer to calculate a chi-squared difference between the synthetic data that we put in ourselves, so we knew exactly what it was, and the image that came out. And so you took the set of parameters that best reproduced, say, a disk, a ring, whatever. I mean, just a series of synthetic objects, and then use those settings on each of these parameters to look at the black hole data. And then you had one of those from each of the days, the 4th, the 5th, the 11th, and the 12th of April 2017. And you could see how those looked. And we took the clean method and made that algorithmic. So instead of having super experts like Thomas Kirchbaum in Germany or Alan Marsher at BU, who are like, super experienced with using this clean method and how to reliably get a reliable image out of subtracting these artifacts, we made an algorithm out of that, and then applied, and then did it with that. So we had these mechanical ways, a mechanical clean procedure, a mechanical exploration of parameter space compared to synthetic data that gave us a top set of the parameters, and then applied that to the data. And we still got the rings. And then we looked at like gigantic number, like 100,000 images of all the different sets of the, and it turns out to be hard to get rid of the ring, of the shadow. So it was a combination of these independent expert judgments based on two radically different methods, clean and the Bayesian forward approach, and then these mechanical explorations, these algorithmic explorations of parameter space based on looking at it all together and just looking at tens of thousands of these things, and then choosing a top set of the parameters based on analysis of synthetic data and applying that to the raw data from the April 2017, and then there were images from each days, and then those are combined in a just averaged in a mechanical way and produces this image. And this is the image that went up on April 10th at 9:07 a.m. in each of the different countries that participated. So this image is super hybrid. This doesn't actually correspond to any particular thing. This is actually an image of all 4 days pulled out of the top set of parameter choices applied to the data in these different data streams that came up through the different methods. So this is what you see when you look day by day is that the 4th and the 5th look pretty similar, and the 11th and the 12th look pretty similar, but there's a shift from here, the bottom left to the bottom right. Here it's kind of mushed together, but so there's something changing. I mean, there's no doubt about it. But then what is it? Is it something that's moving? There's this sort of light crossing. I mean, the characteristic time here is about 4 or 5 days. So it could be that there's something big moving around M87, some big hot spot, or I don't know what. Or a lot of the plasma physics, the relativistic plasma physics modelers think that it's probably the funnel, the swirl that's leading to the jet. So you have the black hole is spinning. It's kind of spinning. We're looking down the barrel of the jet. It's coming like right, so 17 degrees off of directly towards us. But it's fairly narrow as you go far out. But near the black hole, it's a funnel, and it's a pretty big funnel. And that spinning is probably what they think that's what we're seeing. So rather than the accretion disk flow or something else. That's all in the future to be resolved, what it is, but there's something that's changing over time on a period of days. Of that, I feel very confident. Whereas the mass, which is basically determined by, once you have the distance of 53.5 million light years, which seems to be, I'm told, I say this ex cathedra, not because it's something I really understand, but they seem confident that they know the distance, and that then tells you the size of that, which tells you then the mass. So that seems to be pretty reliable at 6.5 billion solar masses. That's much more reliable than the cause of what this brightening is. But the fact of the brightening in the south is very well established across a zillion different measurements. And the change in time on a period of 4 or 5 days seems to be very solid, some kind of Doppler effect of relativistic plasma, probably in the funnel wall, but could be partly from the jet, could be partly from accretion disk. Yeah. So, yeah. So this then gives another kind of boost to the reality of black holes. Now you can say you've seen it, and that's. But if you take seeing this supermassive black hole, all of the studies of both of merging stellar mass black holes and of unseen partner binary black holes and of the theoretical work over time, they do seem to be part of the apparatus of our universe. They have a huge effect on things. At the supermassive scale, they change the conditions under which stars can form. The jets can disrupt the gases that lead eventually to the production of stars. They therefore shape galaxies in this way. There's probably a supermassive black hole in every galaxy, which means there are 100 billion of them in the visible universe. There's a gigantic number of stellar mass black holes, and there's some unknown number of primordial black holes. That's another story altogether. Are you going to talk about primordial black holes next semester?
Nobody knows anything about them.
Okay. Well, if you change your mind, I'll come. I want to learn about them. Anyway, thank you very much.
More questions for Peter?
You know, I think that with LIGO, with the big optical telescopes, which are entering into a new epoch, and with the Event Horizon Telescope, there are 3 very different new forms of observing black holes. And they've really just begun. I mean, LIGO's begun to be able to model some of these. We're beginning to cross-correlate what they see with gravitational waves, with optical analysis. The Munich and UCLA groups are beginning to get even better and even closer to the Event Horizon. The Event Horizon Telescope is now opened up with increasing frequency, therefore reducing wavelength, increasing the number of sites, and eventually putting telescopes in space. They'll get be much better resolution. So I think it's going to be, from the observational point of view, a tremendous time. And I think from theory, as you'll hear about much more in the coming months from Andy, it's a tremendously exciting moment as well. So I think I'm very hopeful. It's a great moment to think about black holes.
Okay, thank you so much, Peter.
Thank you. What are you doing next?